have been working for last 3 decades. When the power analysis we talk about, the contribution of power mostly comes from two things. One is dynamic and the static power. Dynamic means the power which is dependent on frequency. Static means which is independent of frequency. Static definitely has a few parts which can come from different sorts of leakage. The gate can have the leakage, then there can be subthreshold leakage, there can be all the reverse bias PN junction which is happening. If I have a MOSFET device, there are substrate and the source and drain also creates two PN junctions, right? So because mostly those PN junctions are kept in the reverse bias, there also leakage will come. So there are many components of leakage which comes into the picture. So eventually the total power is a function of dynamic power, short circuit power, and the leakage power. From these architecture, we may get a clear idea of how the short circuit power and the leakage power are different. If I look into the right hand side architecture, considering an input equals to 0, you know that your PMOS turns on, but your NMOS turns off. But still at that time, if you get to see some current is flowing from the gate terminal, even though there is an oxide layer which is an insulator, then this is a problem. And also because this NMOS is off, fundamentally no current should flow from the output terminal to the ground. But if you measure the current, you will see that some current is flowing. So these are component of leakage. So for leakage, your device has to be in the off state. At the other end, the short circuit, when we are dealing with short circuit, what does it mean? It means this leakage current is always on the levels, right? Either at the logic high or at the logic low, right? When you are at logic high, then at that time your NMOS is on, PMOS is off, which means at that time this will leak. And at the different level, so on the different level, you will have your NMOS is leaking. But when we come into the short circuit power, there is a transition happening. We are dealing with this particular transition from logic 1 to logic 0 or logic 0 to logic 1. During the transition, what is happening is that one of the devices will be moving from off to on, another device will be from on to off, right? So if we understand the VTC, voltage transfer characteristics of an inverter, we know that at the middle of that VTC, both PMOS and NMOS becomes in the saturation zone. So one is moving from off to on, another is from on to off, and in that process, there is a common zone where both the devices are in saturation. Both the devices are in saturation, it corresponds to you have a direct path from the power to the ground. So basically VDD gets shorted with the ground. That's how the short circuit power comes into the picture. So the more number of 0 to 1, 1 to 0 transition will happen, more short circuit power will come into the picture. In other way, it can be concluded that if for a particular time duration, if frequency is large means time period is smaller. So you will have more number of switching. So more number of short circuit power component will come into the picture, right? So that is how your short circuit and leakage are different from one another. Now, in this particular discussion, we are mostly focused on the leakage component that basically, if we understand the ITRS roadmap, International Technology Roadmap for Semiconductor, we have seen that when the technology node is lesser than 45 nanometer technology, at that time, we have seen that the component of dynamic power is either equal to static power, static power or leakage power, or leakage component is increasing because of very small dimension. It is also one of the short channel effects. So the focus towards the leakage or static has been more prominent for the lower nodes. So for that reduction, there have been quite a few techniques called clock gating. Clock gating is a technique where what we are doing, but for a synchronous sequential circuit, we know that the moment clock hits, then only data will process, right? So every time clock is hitting and then one data moves, right? So if you have n number of data, n number of times data should hit. That's the basic understanding of any synchronous system. But what if, for example, all the input datas are all same? For example, all are 1 for a long duration, or all are 0 for a long duration. At that time, even if clock is not hitting, your output will remain same only. So it means if at any instant the input which is waiting and the output already available at that instant, if they both are same, the clock is not needed to hit the device. We can prevent the clock to hit the device. That is called clock gating. So by that process, we can reduce the unnecessary switching because of the clock, and the power reduction can be attained. So there are other methods called dynamic voltage and frequency scaling. There will be a different control circuit which will scale down your VDD as per requirement, because we know that if my VDD is lesser, my power dissipation will also come down. But the problem is with the scale down of VDD, your delay will increase. So if your core is performance heavy, which means you need efficiency in the speed, you cannot cut down the VDD as per your necessity, because it will enlarge the delay, right? Latency will be increasing. But if your core is power dominant, means your design is targeting the power only, not performance, then you can cut down your VDD till the lower VDD at which your circuit will work. So there is a control circuit which can understand that which subsection of my circuit is performance dominant, which subsection of my circuit is basically focusing on power. So accordingly, we can dynamically scale my voltage and frequency. But the problem in this method is your controlling circuit becomes huge. So for any small logical core, because your controlling circuit is large, combining both, your effective power dissipation becomes huge. So this method is only valid for large or big size of core. There are subthreshold operation. Subthreshold operation means when your VDD is close to your threshold. So in the subthreshold operation, again, you can only focus on the power focused design, not the performance focused design. Adaptive body biasing is a technique at which the bulk terminal, basically any MOSFET is a 3-terminal device, but at that time we are not focusing on the bulk terminal or the body terminal. In the adaptive body biasing, the body is being biased through an external potential. And we know because of the body effect, depending on the potential we are applying at the body terminal, my threshold voltage will get changed, right? So if the threshold voltage is getting changed, you will definitely have impact on both power and delay. Because if the threshold is large, your power dissipation will be low, but your circuit will be slower. If threshold is lower, your power dissipation will be more, but your circuit will be faster. So always we need to do kind of trade-off. But the problem in the adaptive body biasing is leakage becomes huge. So this method is not considered or it does not carry potential in the lower nodes of design. Sub 20 nanometer technologies, for example, we are designing in 14 nanometer, 20 nanometer or 10 nanometer. I mean, these methods are not that encouraged. Multi-voltage design is also a method similar to dynamic voltage scaling, where as per the requirement, means before designing, as a designer, we will decide at which sub-block what VDD to be incorporated. And accordingly, we can only optimize the power out of it. And the other method is power gating. In power gating, what we are doing is we are trying to I mean, very fundamentally, for example, you have a logical core and you have a power supply here. Fundamentally, power supply is always connected with the logical core. But what we are doing is, between VDD, which is power supply, and between the logical core, we are incorporating another third party based on some NMOS or PMOS. Okay. So when I need, then I make my switch on. So VDD will get connected with the logical core and current flowing will start. And if I don't need, at that time I will keep my switch off. So VDD will get disconnected from the logical core. That's how power getting means power is sent through some gates. And as per our requirement, we will allow the power to happen. So this method has some, merits and demerits. Definitely leakage power preservation or leakage power optimization can be done. But major two problems are the switch which we'll use, that size of the switch has to be very large. Why? Because that switch should be able to draw a large current which is drawn by your logical core. For example, you had a circuit which draws a current of 10 milliampere, right? So now, because in between power supply and the logical core, I have connected another third party. So that third party also should be eligible to draw 10 milliampere of current, right? So, but this 10 milliampere is coming from a big network of circuit, right? Now I need to draw that 10 nanoampere current using a series of a parallel connection of PMOS or a parallel connection of NMOS. So the sizes of those devices has to be quite large. And second important problem, which is hardly attended in literature or any recent research, is when suddenly you try to make something on or off. No, there will be sudden, see, for example, you have made the switch off. So there is no current flowing. And suddenly through a signal, you have made it on. So from an on to off state, a sudden rush of current will flow. It is similar to, for example, you are sleeping and you are in a deep sleep, right? And somebody has pushed you to make you wake up very abruptly. It will definitely happen that if instantly you wake up, your brain will not process what to do. You will get confused. But if you are made to wake up slowly and gradually, that problem more often than not will not happen, right? So power getting has that problem, that because in a flash of a moment, we are turning it on, change of current, DIDT, is huge. And I'm sure if you are comfortable in the power electronics, you might have heard about LDIDT noise, right? In any communication from VDD to core, there are some RLC lines I'll discuss. There are many L's are available. So LDIDT noise comes into the picture, which is also called nothing but supply noise. So we need to focus on that also, that how that supply noise can be minimized. So power getting has these issues, but for the leakage power optimization, it is definitely a good technique. Now what we do in the power getting? See this circuit. I have written something called internal circuit. Internal circuit is nothing but your logical core. Here see VDD and ground, these are your power lines, right? And between your internal circuit and VDD, I have connected an PMOS. This is my third party. And here, between the internal circuit and ground, I have connected a third party. So if you want to do the gating based on PMOS, it has to be connected between internal circuit and VDD. If you want to do it between internal circuit and ground, then it has to be done by NMOS. Now it can be a single NMOS, it can be a many parallel connection of NMOS depending on the requirement, right? So if we are doing based on PMOS, definitely if at the input of this gate, if it is 0, The PMOS turns on and VDD is getting connected with the internal circuit. Means your device is powered on. If you give an one signal here, then your device will be off. The situation is just opposite if you connect an NMOS. The moment you give an logic 1, your device will get connected with the internal circuit, which means turns on. If you put a 0, then your internal circuit is disconnected from ground, which means the device is off. Right? So that is how the power getting comes into the picture. Now, when we are doing this design of power getting, quite a few things we basically need to take care of. One is power gate size. Power gate means that PMOS or NMOS, the third party element which we will incorporate. As I mentioned, that gate size has to be very carefully chosen, because that gate or that PMOS or NMOS should be able to draw that much of current which is drawn by the internal circuit. So choosing of gate size is very, very important. Then the second point is gate control slew rate, means how fast or how slow your gate will turn on. That slew rate is also important. Depending on that slew rate, we will also have an analysis of my LDIDT noise, right? Because slew rate will define the DIDT, and because in the path of VDD to internal circuit you already have L, so there will be LDIDT. Simultaneous switching capacitance, what are they? See, if we know when I have a MOSFET is surrounded by many parasitic capacitance, gate to drain capacitance, gate to source capacitance, gate to bulk capacitance. The bigger the size of the MOS will be, the bigger the capacitance will be, right? So if the capacitance is getting large, signal flow will be slower. You can think of as an RC circuit. You have a path, means you have a resistance. You have a gate, which means you have a large capacitance. So you have an RC. So if in your communication path, if you have more number of RC, you will have more delay. R multiplied by C, we know it is nothing but a time constant, right? So it produces the delay over here. And thirdly, the power gate leakage. The bigger the circuit, the more area for the leakage to happen, right? So leakage current also increases. So one thing we need to take care of, the power getting we are doing for the reduction of the leakage of the internal circuit. But because power gate size has to be large, that third party itself will start leaking more. So you really need to balance, right? So logically or theoretically, even though the concept looks pretty straightforward, as a designer point of view, it is very tricky. Very minutely, you need to set all the parameters before analyzing the circuit, whether your method of power getting is working or not. These are the discussion of all the methods which I have done. Now, this is one point to be discussed, that power getting are fundamentally of two types: fine grain and coarse grain, right? Fine grain and coarse grain, they are basically nothing but, for example, you have a system, right? This particular system means, for example, you have a big internal circuit. Now, this internal circuit will have many sub-blocks, right? Inside every subblock, you may have many standard cells. Standard cell means, for example, NAND gate, NOR gate, XOR gate, like this, right? So, for example, you have 3 layers: main block, many subblocks, and inside the subblocks, many standard cells. Okay. If the power getting is incorporated for every standard cell, means every standard cell is separately power gated, it comes on the fine grain power getting. If only subblocks are power gated, means internally every standard cell is not power gated. only a single subblock is power gated. So if the power is not going, then entire subblock will not get power. It comes under the coarse grain. Okay. So coarse grain focused on the subblocks, fine grain is focused on individual standard cell. Now both these concept of fine grain and coarse grain power getting are again can be done in two ways. One is ring based, another is column based. Now this is mostly related to layout, right? Not in the circuit specifically. In the layout, you can think of this arrangement. If you see the left hand side, right, all these boxes are subblocks, right? The blue lines are the power line, and from that power line we are bringing the power to the internal subblocks through some PMOS, right? If the arrangement is like this, it is called ring. If the arrangement is like the right hand side, right? See from the blue power line how we are bringing the power to the circuit. The red lines are circuit VDD, right? So if the configuration is like this, it is called column based. These are just ways of, now there is no, I mean, you cannot ask the question of which method is better, ring based is better or column based better. It is not like that. The moment we do the layout, depending on the space requirement in the given wafer, we basically will place my layout standard cell, and depending on the placement, we have to decide that if we do ring based or column based, which will give me the optimized amount of the metal layers, right? So accordingly, we decide which way of power getting we need to go for. Now, this is the important point to understand that in this lecture, I'm more focused on explaining the problems. The few solutions we have done, I'll just explain the logical architecture. See, try to focus on both left-hand side architecture and right-hand side architecture. In the left-hand side architecture, I have shown the current profile for a logic circuit when I'm turning my internal circuit from off to on. See, if you see the time frame at an instant of 2 nanosecond, this is the instant where I have turned my device on, right? The same figure only replicated on the right hand side also. Here at 2 nanosecond, I have turned on from off to on. At 6 nanosecond, I have turned it off from on to off. In both the cases, if you see, current is settling down here, right? Around 1 milliampere. But see, during the instantaneous switching, current has doubled. It is gone up to 2 milliampere. And doubling of an specification, for example, you have a device, you have purchased a device where the specification is 10 milliampere, and instantaneously it is hitting the 20 milliampere, your device will burn out. Your device will never sustain. And also think of the DIDT at that instantaneous time. DIDT means change in I divided by change in time. Change in time is very small. Change in I is huge. And very practical example of it I can give you, we might have experienced that, for example, when we connect our mobile charger or laptop charger in the sockets, electrical sockets, during the connection, you might have seen some spark, right? And we basically tell it, there can be some short circuit. There is no short circuit actually. What is happening inside the socket? You have a cylindrical metal, right? And the pins of the laptops of charger which you are inserting, that is also a cylindrical metal only. So when you are inserting, actually, the cylindrical layer of the socket and the cylindrical pins which you are inserting, they have an air gap between them. So one metal line from the pin, another metal line from the socket, in between air gap, they suddenly create a parallel plate capacitance. And very instantaneously, they get charged up. The moment you fix it properly, there is no capacitance. That capacitance quickly discharges. That quick discharge is so large that the metal wires cannot immediately ground it. And the electric field is thrown to the air. And that we see as a spark, right? So that is a very basic or real-time example of this sudden spike. So these spikes in the electrical circuit, or another example is you might have seen that the PC which you are using in day-to-day life, in our labs, or we might have observed that SMPS has gone wrong, right? Why SMPS will go wrong? This will definitely happen that your original power supply might be fluctuating continuously. If it is continuously fluctuating, your your SMPS will always experience this kind of surge, this kind of spark. And if that happens, basically from the specification, instantaneously the current which is coming is huge, and that's actually burns out something inside the device, and thereafter it doesn't work. So it is available inside VLSI circuit also, right? So this is a big problem, and this is a problem which is hardly attended if we see in the literatures. And for last 5 to 10 years, industry have been exploring quite explicitly in these particular areas, because in the lower technology node, your device is very small. Already for last 20 years or 15 years, we have been using 180 nanometer technology or 250 nanometer technology. But these days, Intel, IBM, and even the TSMC technology provider, they are building 2 nanometer, 5 nanometer, 3 nanometer technology sizes. You think of the device, right? Any small fluctuation of current will create so strong electric field that your device will be shorted. And then thereafter, that device will be of no use. So you need to be very careful in terms of minimizing these things. So how we can solve it, right? There may be many methods, but how we can do that, right? You see, there are fundamentally two methods. One method is modulation of the gate voltage. Modulation means variation of the gate voltage of that transistor, power MOSFET, or sometimes it is also called the sleep transistor. So the gate voltage, see at the gate voltage, what it is happening? It is suddenly switching from 0 to 1. 0 to 1 means what? If your VDD is 1.1 volt, for example, so it is switching from 0 to 1.1 volt suddenly, or 1.1 volt to 0 volt suddenly, right? So rather than suddenly changing it for a very small time duration, can we change like this, that from 0 to 0.3, 0.3 to 0.6, 0.6 to, for example, 0.9, then 0.9 to 1.1, like that, for example, right? So what will happen? The instantaneous jump of voltage is not large. So there is a possibility that the ramp of current, or DIDT, can be reduced. The second option is delay based. What is this delay based? Delay based means, see, instantaneously when you are giving your rise time 0 to 1, it is 0 to 1, it is reaching maybe in a time of 10 to 20 picosecond, right? But our real time work is happening in the seconds. So picosecond to second, there is a huge gap, right? So can we play in such a way that that picosecond rise time can be enlarged to maybe nanosecond, to max of microsecond? But still in the naked eye, we will never understand that the device is slow or what. And expectation is you slow it only during the switching. After that, the device will work as it is. So these are the ways. So what is the point? If you, so you can think of here, the plan A is the conventional, means suddenly you are switching, so suddenly you will get some current. The plan is you give some time during the switching. So current will also gradually increase. So at that time, what will happen? That sudden surge or spike, there is a possibility that it will get eliminated. We'll see. Now, in survey, if we focus on, for example, these methods, that modulation of gate voltage, there are many different methods, like power getting with data retention mode, which has been done using a diode, power getting with data retention mode where MOSFET is used, eliminating the diode. Then people have come up with the concept of multiple sleep modes. Means initially people are thinking 2 or 3 jumps, like 0 to 0.4, 0.4 to 0.8, and then like this, right? 2 to 3 jump. Then people have increased the number of jumps, right? Multiple modes they have created. And by this process, they have seen that some sort of betterment is achieved. So we can see the first architecture looks like this. This is the internal circuit. See here, the gating is being done at the footer. Footer means between the internal circuit and the ground. Okay. So because of this diode will always clamp a potential which is nothing but the threshold voltage of this particular device. If the threshold voltage of the knee voltage of the diode is, for example, 270 millivolt, then there will be an gap of 270 millivolt at the ground terminal. Means at the ground terminal, you will never get logic 0 at the output. Over here, you will never get an, see, when the output is switching from 0 to 1, right? What we are getting, logic 1 is nothing but coming from the VDD. Logic 0 is nothing but coming from the ground, right? So because of the incorporation of this diode, the V ground terminal will never come down to the ground. It will always have a potential close to 270 or 280 millivolt, which is nothing but the knee voltage of your diode. So what is happening in this method is, if you see, your logical operation will happen, but because the lower logic level is not reaching ground, it is coming to 270 or 280 or, for example, 300 millivolt. See, the peak-to-peak voltage has been reduced. If the peak-to-peak voltage has been reduced, because initially if the VDD is 1.1, your ground is 0, peak-to-peak is also 1.1. Now peak-to-peak will be 1.1 minus 270 millivolt or 280 millivolt. So because this is reduced, your power dissipation will also come down. This is one method, but again, these diode incorporation do not have any external control. So people have moved to, they have converted this diode using a PMOS over here. Okay. You see, if you put S1 equals to 0, no, S1 equals to 0 means S1 is connected with ground. So at that time, this PMOS is actually nothing but a diode connected PMOS. So it is the same circuit of the diode, but they have brought some control through the pin of S1. So whenever needed, you can create it work like a diode. Whenever not needed, you can basically remove it. So from these methods, what we have seen that the main objective of reducing that current shoot up is not solved properly. So people has actually gone to multiple step modes or multiple sleep modes. See, here there is another circuit. This is an internal circuit. This is the sleep mode. In all the previous mode, what is happening? We are trying to vary, or we are trying to modulate the potential at the gate. Okay. So how we are going to vary? We are going to vary depending on the polarity we'll put at these particular nodes of S0, S1, S2, and S3. Right? For example, if I put S3 equals to 0, no, so this M3 will turn on and the full VDD you will get at the gate. For example, if S0 is given 1, so this M0 turns on, this is an NMOS, so the ground will get shifted to this gate. Right? If S1 turns on, through M1, this V1 potential, some potential will come into this gate. If S2 turns on, this V2 will come into this gate. So we have achieved 4 different voltage levels at the gate, right? There are 2 problems in this circuit. One problem is this voltage V1 and V2 has to be generated through some external potential, but when you design a chip, inside the chip, the potential will not be provided from the external world. You need to design some circuit for the generation of those voltages, right? So you need to have 2 different bias generator circuits, and bias generator circuits are nothing but analog designs, and eventually the total requirement or total size of the circuit is actually increasing. There is another problem in this particular circuit. Another problem is we have seen that this through M0 we are getting ground, through M1 we are getting V1, through M2 we are getting V2 at the gate. These ground V1 and V2, they all are some potential which are less than the threshold voltage of this M slip, means this power MOS. Due to which what is happening, if the threshold voltage is, for example, 300 millivolt, V1 may be 100 millivolt, V2 may be 200 millivolt, right? So one jump is 0 to 100, second jump is 100 to 200, right? Think of the third jump. Third jump will be 200 to VDD, which is 200 millivolt to 1.1. So, though at one side the jumps are slower, at the other side jump is huge. And you see the current profile. This is the instantaneous current profile. See, here the jump is huge. And the current ramp, which is DIDT, we are getting 11.49 mega ampere per second. And the second jump is only 0.37 mega ampere per second. Means a few hundred times larger. So this kind of designs are not expected. Whenever you are designing in terms of certain jump, you need to try out that how uniform your jumps are, right? So there is a research gap here. This is one problem statement one of my research scholars has worked into, and we have come up with a different method of generating the 4 voltage levels only. One we are generating through this M1 with this feedback connection. One is similar to the previous connection. Everything is same. See, this M0, M3, M2 are exactly same to the previous work. Only this connection of M1 we have improvised. And by doing that, what we have achieved, see the jumps of the potential in this graph. 58 millivolt, which is logic 0. See, in real life, you will never going to get 0 at the logic level. You will always get 20, 30, 40 millivolt. So we are getting 58 millivolt. And the second jump is 426. Third jump is 650 millivolt. And then the next jump is 870 millivolt. And then we are going to 1.1. By this process, we have actually minimized the ramp of the current. I think somewhere we will show how the ramp of the current has changed. So these are some analytical data. I'll mostly try to skip them. Just telling you what analysis we have done. We have basically fixed the supply voltage and varied the temperature from -40 degree to 120 degree centigrade to see what is the stability of the circuit. Why it is needed? It is because whenever you are designing a particular chip, right? And if that chip will be incorporated in any circuit or any device, for example, your mobile or any other gadgets, right? You may live in India, you may live in America or countries like Korea, China, or Japan. At different countries, the variation of temperature is different, right? Your countries like Russia can achieve even the minus 50 degrees centigrade or minus 40 degrees centigrade, right? And countries like Africa, or even in our states like Rajasthan, Delhi, we are getting touching 50, right? So it is the atmospheric weather I'm talking about. When the device is in computation, you might have seen your laptop is shooting some heat, your mobile gets warmed up, right? So the device junction temperature also increases, and it is more than your weather temperature. For example, today you are sitting at 40-degree at Agartala. If you feel is your mobile is hot enough, which means your mobile temperature is definitely more than 40-degree. It might be working in 60, 65 degrees centigrade, right? Otherwise, you would not have felt the temperature or hotness of that particular mobile.